control. Now the background of structure. So as I told you, it composed of a large number of sub-wavelength elements, and so it can control the electromagnetic property of the incident wave. Now, if in the classical communication, let us say that, so if these are the two buildings and we want to have the communication between the transmitter and receiver, so if the transmitter is there, so let's say, so there will be reflection from the building and signal will getting decayed. So, and you will get some, at the receiver, you will get some signal, but it will be very less. Now, instead of having, if I deploy an RIS on this building and on this building, so what you will have, so you will have the communication between the transmitter and the faithful communication between the transmitter and the receiver. So you'll have the communication. So, and this RIS, so what, instead of scattering in a all direction, it will try to scatter only in this direction. Similarly, this RIS will scatter in this direction. So you'll have the faithful communication. Only just you have to adjust the, because the energy is already there. Only just you have to change the direction of the energy or of the electromagnetic wave by putting some reflector or RIS structure is there. So RIS is a key potential technology for the 6G communication. Now, history of RIS. So metamaterial started a long back, that is 1967. Then the Russian scientist Veselogov gives its name metamaterial. Metamaterial means something which doesn't exist in the nature. Meta means beyond nature, and material is material, just so which exists in nature, doesn't exist in nature. So, but it will have with some unnatural property. So we can achieve these things by, we can achieve that property by, means by having, by using some materials. So now so that is negative. So the two-dimensional equivalent of the metamaterial is metasurface. So this was used in physics. Now people have moved to the, that is in the electromagnetic domain. We call it metasurface, two-dimensional equivalent of the metamaterial. So there are different types of metamaterials. So that is people have designed, that is electric, magnetic, thermal, light sensitive. So we are, as we are discussing here, so it will be just electric or magnetic meta type of materials we will be discussing, which will be having the just a pin diode or maybe some structures. The patches are there. So that is of the dimension sub-wavelength. So now, so this RIS can be viewed as a reflective array of composed large number of sub-wavelengths. So if you see here, so this is the RIS structure. So what would be the beneath that? What would be the beneath that? Below that? So below that you have a phase shifter and a phase shifting circuit, basically with a vector diode. Now, if the thickness, so what we want to have, so we want to have, let's say, if I feed from 0 degree, and if I want to have beam in a 0 degree direction, or in maybe the beam is in this direction or 30 direction. So what phase each RIS elements, that needs to be decided. So that has to be decided, or that has to be decided by the biasing voltage. I will discuss. If we change the biasing voltage, the phase can be easily changed. So that is by, phase can be easily changed. Okay, so this is the, so now people have demonstrated the RIS prototype. That is in the China, Japan, India also we have demonstrated. That is IIIT Bangalore has demonstrated the RIS along with the IIT Roorkee. Its communication group has demonstrated the RIS surface. So they have in the form of frequency field painting, then at 2.3 gigahertz, and all these things they have demonstrated. Now, this RIS aided communication, it overcome the blockage, it provides additional communication link, enhance the signal quality, increases the spectrum efficiency, save the power consumption, increases the energy efficiency. So now, if a transmitter is there, if this user is there, so now if there is, this user, we have the direct path, and another path is from the RIS to this user. Similarly, for this car, so instead of having this one, so we have from RIS to this one. So this will enhance the energy efficiency, or the user will get much more clearer signal than the other ones. Now, if I compare the RIS with the active relays, so relays are two types, that is decode and forward. Decode and forward means just so relays are basically they region decode. Decode means whatever the signal you are sending, convert into the baseband, and then again retransmit, regenerate the signals. So then it can be transmitted. Relays are there. Then amplify and forward. So amplify and just so they will just amplify and forward it. So now, so what is the difference between that? So if you use relays, So because the noises are there, so noises are there, so noises will also get amplified. So they will also get amplified. So you will have the noise, signal to noise ratio will be lesser here. But in the RIS, so we are not converting into the baseband. So we are uh, just just moving the direction of the signal. So we are not adding any noise. So we are just getting, so we are not degrading the signal to noise ratio of the whatever the desired signal. Okay, so now, so this is, so, okay, one more thing. So based on that, so if let's say if the receiver is far enough, so we can have the active, that is generally the RIS structure is passive in nature. So the we have the, because at the back we have the vector diode and the capacitor is there at the back. So if the receiver, let's say if you are not getting good amount of signal at the receiver, so you can use the active RIS. Active RIS will have the reflected signal with the amplification. So it will amplify the signal also. So here reflection type of amplifier is used at the back. So it will have much more larger power consumption than the passive RIS. So there are different types of active reflection type of power amplifier. Okay, so now what are the RIS applications? So as I told you, RIS applications have, as I told you just earlier, so that is metaverse, industrial, that is the ADAS, automotive driving car assistance system. Then we have for the intelligent transport, ITS we have, that is intelligent transport and intelligent manufacturing, and then robotic surgery, all this can be used. Now also, that is about the application for 6G. Now, how it can be enabled? So this RIS can enable, or it can be means it can enhance the feature of the 5G network, already existing the 5G network, or it can be used to increase the enhanced communication in the indoor network. As I told you, just mount the RIS wall inside the building, you will get the good amount of communication. Or you can have the, in the, let's say the unmanned system, means just because this is fictitious, or you can have the intelligent IoT network, means all the devices can be connected to each other. So you can have the communication. Okay, so these are the some of the applications of RIS. Now, what are the advantages of the RIS? So, with compared to the existing architecture generally, the, if you see the, we use the, that is phased array are used for diverting the or beam steering, or the reflector type of antennas are used. So here we use the something like maybe that is meta surface. It is called meta surface. So meta surface type of antenna. So it is, so what are the advantages? So its cost is low compared to the all other, because, and its weight is also less. Okay. And its reliability is much more higher, and because it is having no moving part. Here the phase there is also no moving part, but because of the changing of the temperature, so it will be yeah, it will be, reliability is somewhat lesser. And DC power means it requires small DC power just to tailor the beam, and it will have the small form factor compared to the others one. So it is maybe in, that is why in the coming future the RIS is coming. Now on the conventional RIS, so conventional transmitter, what we will have, we have the, let's say if you talk about the massive MIMO, so we have the numerous antennas elements are there. So it will transmit the signal here, transmit the signal. All that number of transmitters are there connected to that. While this in the RIS structure, so you will have the one transmitter signal here, and some modulated signal will be there. So some, whatever the programmable meta surface is there, so it will retransmit the signal, RF signal, to the desired direction. Okay, so it can be used for beam steering, beam splitting, adaptive beam forming. It can be used for that. Now the question comes. So now I will just, so this is some of the structures where people have designed it. So this is basically some RIS structure is there. So they are exciting from the one of the horn antenna, and its beams can be transferred to the desired direction depending upon the, now the whatever the data source you feed, whatever the ones zeros, which patches you excite, depending on that it can be excited. Okay. Now, if you have any questions, you can ask me till now. Otherwise, I will move to the second part of my presentation. Okay. You can ask the questions if you are related to the basics of RIS structure. Yes. Hello. Yeah. No questions. Okay. No questions. Then I will move further. Okay. Then I will move further. Okay. So let me then I will. These are the some of the how RIS is used. Now I will tell you how we can design some of the RIS structure. Okay. Let me show you them. Okay. So some of the two things which our group has designed, so that we will discuss here. That is 2-bit tunable unit cell for quad band reconfigurable intelligent surface. Okay, so now let us do that. So it is so basically, as I told you, in RIS, the simplest is just a patch. RIS is just a phase shifting network, phase shifting structure. So here it is a patch. Okay, so here, no, sorry, it's just a patch, and on the patch beneath, you will have the varactor diode, or maybe some unit cell. So some people call it unit cell, some people call it meta atom. So what I have just said, so first you have to design the unit cell and study its behavior. So let's say here we have what we have designed. We have designed a unit cell here. So the unit cell is composed of, so this unit cell composed of a patch, central patch, and two, four U-shaped structures, and some connecting structures are there, and then a metallic ring outside, and this one, then this structure, whatever this protrusions, and in between we apply the vector diode. If you apply the vector diode, so this, and we have the VRs which are shorted at the end. So you have to study the unit cell behavior in the ANSYS, HFSS, or CST by using the Floquet boundary condition. So what would be its phase? What would be its phase change for different frequencies or different biasing voltage for this capacitor? So that is, so as we have used BB857, so capacitor from the data sheet. So from the data sheet, that is 0.8452 to 7.2 picofarad. Capacitance can be varied by applying the bias voltage of 1 to 28 volts. You can vary the voltage. Now, based on that, let's say for different coding state means, so for okay, so now here in this case, coding state means what I mean to say, the coding state means for different values of capacitances. So what we have taken here 6 states, that is we have varied the capacitance into 6 different values from the, that is 0.612, that is 0.62, 0.95, and all these things, and you try to plot the magnitude. Try to plot the phase response, that is reflection phase response, and the magnitude response, the reflection magnitude. So if you see here S11 in dB magnitude, that is reflection of the reflection magnitude, and the phase of the reflected signal. So what you can observe from here, so this is, if you see this one, so it is, we have plotted from the 2 to 10 gigahertz. So 2 to 10 gigahertz, it is plotted here. So from 2 to, so the reflection will be very less, because it is just because it is something similar to the perfect electric conductor of PEC, or maybe just 1 or 2 dB will be there. So basically it will be entirely reflecting the signal. Maybe just we'll have that some dips are there of, that is 1 or 2 dBs are there. But the important thing is that the phase is changing very, the reflection is very less. That is, sorry, reflection is all the signal will get reflected. But the means that is all the power is getting reflected. But the important thing is to see that its phase. Phase changing is this, you can observe the phase change. So it will have different phases at different frequencies. So you can see the zero phase at the whatever the two, that is 3 gigahertz, and if we move further higher than frequency, different phases. So it is, we have unwrapped the phases. So basically the phases, it's having the different phase changing behavior. Now based on that, so since it has the resonance at 4 structures, 4 points, so that is 3.5, 5.1, 5.84, and 8.4. So resonances, that is -2 dB if you observe it. So it is a zoomed view of that structure. And this is the this is the phase of this one. This is at the first, that is 3.5, then 5.1, 5.85, 8.4. So you can observe the resonant frequency is also getting changed and the phases are also getting changed. Now, but if you see one frequency, let us say that if I see the frequency 1, if I see the frequency of 3.5 gigahertz, so at 3.5 gigahertz, each state will have different phases. Magnitude doesn't contribute much, but the phase contribution is much. So if you see observe the phase at 3.5 gigahertz, so this one will have the phase of something, let's say the phase of -180 degree, this one will have phase of 90 degree, this one will have 0 degree, then 90 degree. So you can have all the phases variation with respect to the whatever the basic condition of your vector diode. Similar things happens here also for different states, different biasing states here. That is 5, 6, 7, 8. 5, 6, 7, 5, 6, 7, 8. Here also for different biasing state. If you observe at 5.1, again you will have the phase of 180 degree, then this one, then this one. Basically phase changing. Phase, that is 0, 180 degree, plus 90 degree, minus 90 degree. Phases can be observed. Similar thing happens here. All the things can be observed here. So now, okay, so add all the 4 frequencies, we can have the different phases can be observed. So based on that, so you can plot the signal. So S parameter, as I told you, S parameter is not of the important. So S1, so we can, important is the phase. So you can achieve different phase configuration, different phase angles at different phase, at different biasing voltages of the vector diodes. Okay, so now it is just to show you that just which part of the unit cell is responsible for the reflection. So let's say if this is the smaller part, so this longer part, outer ring, is responsible for 3.5 gigahertz. The smaller part is responsible for 5.8 gigahertz, and so on. So now based on that, so just we have modeled its equivalent circuit and based compare it with because equivalent circuits helps much more. So that is, if you observe that, so you can have the different angles will be there. Okay, so now what we want to, so we have designed the unit element, and the unit element we are able to achieve different phase shift at different frequencies. That means we can change our phase, we can change the phase of the reflected signals if we apply the proper bias voltage to the proper reverse bias voltage to the vector diodes. So now, since we have to excite that, so we have to make the RIS structure first. So let me first make the RIS. So this is the RIS structure. This is 20 cross 20 RIS structure. 20 cross 20, just unit cells are placed with very small distance. 20 cross 20 unit cell. Now, for that, so you have to excite all the frequencies. So frequencies are, if you see, the frequencies are 3.5 to this one. So since we do not have the horn net much more frequency, so we have used this antipodal antenna. So antipodal Vivaldi antenna. So it operates from 2 to 10 gigahertz and have the directional beam characteristic. So this one. So we have placed at the phase center of that is at the focus of this one. This is Vivaldi. Then now let us see what is going to happen if we launch the electromagnetic signal. Then what is going to happen to this signal? So it will get reflected, or whatever it will get reflected, and in which direction it is getting reflected. Now, as I told you, depending upon the bias voltage. Now, so this, what we have plotted here, we have plotted the phase change. So if you see the white one is having the 0 phase. It is something. This is 20 cross 20 unit elements. 20 cross 20 in the x direction, 20 in the y direction. So it is at the center. You have the phase shift of near about 90 degree, and after that you have the phase shift of 270 degree. 270 degree. Then phase shift of 0 degree, and so on. So basically, So this is for the if you excite whatever the anti-Vivaldi and antipodal AVA, that is antenna, with this one. So what you will get here, you will get with 0 degree. So you will get a beam at 0 degree. So at RIS. So if you compare the Vivaldi antenna with RIS surface, so now your earlier the gain was the Vivaldi antenna was the 10 dB. Now it has increased to because of the signal, because of the whatever the signal has increased to the 15 dB. Gain means, so gain, it is acting like a reflector, so it will be focusing much more power in one particular direction. So you will not get. Now this will have the beam in the 0 direction, that is theta equals to 0. Now if you see here, the we have plotted for the theta equals to 40 degree. So you will have the another beam will be there, so it will have the two beams, one it will be at 0 degree. For this you require this type of phase contribution on the structure. So what you can see here, and for that is for G minus 20 degree. So you'll have, we are not plotted. So what we can see that, so your beam can be means if I just change the phase by using some if I change the phase of the RIS structure, earlier my beam was at 0 degree, now it has moved to the, that is 20 degree, and moved to the, that is 40 degree. So just not much more visible at lower frequencies. But if you move to the higher frequencies, if you see here, as you move to the higher frequency, that is at 5.7 gigahertz. So the earlier the gain of the Vivaldi antenna was maybe 7-8 dB. Now at 0 degree it has enhanced, it has increased to maybe 15-16 dB. Means it has increased, the gain has been increased, gain of the reflected signal has been increased to the maybe 10 dB increased. Yeah, nearly about 10 dB. And these are some of the profiles of phase profile. These, again I will repeat you, these phase profiles are obtained by applying proper bias conditions in the vector diode, this one. So we have not decoded it, so we have because we have not we have designed the system, but we were not able to implement it. Implement it using the practical implementation. Okay, now you can see that your beam can be shift, or beam can be shift. So we have not moved anything, just you change the zeros or ones bias voltage of the vector diode. Your beam can be shift, or you can steer the beam in one particular direction. That is used for RIS structure. Similarly, for as you move much more higher frequency, so it can be, we will have larger gain, because at a larger frequency gain will be larger, because aperture area remains same, so gain will be larger. So you can see that you can switch your beam to the from 0 to minus 80 degrees. So it can be switched from this one. So you can, different beams can be switched here. Okay. So now based on that, so if we compare, so we just compare this one. So different gains can be different gain, higher gains are observed, and beam can be steered from minus 22 plus minus 22 plus minus 80 degree from 0 degree. This one. So this we have published it. Okay. So now, so this is one of the work which we have done. Okay. So now. Okay, now, so this you can think of, or you can think of your RIS structure can be, means you can design the RIS structure and you can have this one. And this is another work which we have done, that is 3D printed high gain beam switching transmit array. So as RIS is used, so transmitting array remains the transmit array antenna utilize the properties of RIS. So what we can see, so here we have used some dielectric profile, means some air is there, then we have a dielectric. So it will be air dielectric material will be there. So if you launch electromagnetic wave from here, so if you received it here, depending upon the length of the depending upon the thickness of the dielectric, you will get the phase shift here. Similar thing we got in the RIS structure. So this will be your transmit array here. So now based on that, so this is, so we have designed this transmit array, and you can apply, you can feed your whatever the you can. So we have applied the 7 ports are there. So you can, if you can feed your antenna at this port 1 to port 7, so we will observe what is going to happen. So we have not shifted, we have not changed the anything. So we will show you. So this is, we have used the using 3D printing technology. So I will skip this one. So now if you observe here, the unit cell design is very important. So if you observe, the as the thickness of the unit cell increases, as if there is no unit cell, so you'll have the 360-degree or 0-degree phase shift. Now if you go and increase the thickness of the unit cell, your phase change will increase, or phase, you will have the phase change will be there. So that is, if we have designed it at 28 gigahertz. Now for, if I want to, so here in this, what we, let's say we have designed, maybe that is 16 different states are there. So, and each state will have different phase shifts are there. So for these things, so what we'll have, we have designed 16 unit cell with 22.45 by 2 gradual phase change is required. So for that different, so we'll have the 16 different types of unit cells. So now you place your unit cell depending on the requirement. So this is for the 0-degree. I mean, that's quantized. There is 40 cross 40 unit cells just placed at the your whatever the antenna at the center. So if you place it antenna at that sector, so you will have the one that is pencil beam, very high power. That is, if let's say if you place an antenna at port 4, so you'll have the that is pointed, the broadside direction, you have the pointed beam. Now if you place at 1, 2, 3, 4, that we will show you here. So if I place P1, P2, P3 here, so your beam can be switched to one particular direction, change to the one particular direction. So here you have to place numerous antennas, but in the RIS you don't require numerous antennas. You have to just place the one single antenna and change the structure. So this is called beam steering transmit array antenna. So now we are able to achieve the gain of that is 22.5. Now, if you compare the RIS with the massive MIMO, that is massive MIMO structure, as I told you, in the massive MIMO, you require RF chains are there. So numerous RF chains are there. They are required, and so require the hardwares. Lot of hardwares are there. Hardware are required, but here you don't require anything. Just you require surface and RI surface, because transmitter is already, because you have to already transmit the electromagnetic signal. Here you don't have to transfer it. Means you don't require large number of transmitter. So it is basically re-radiate the signal. So the complexity is less, power consumption is less, and it is easier to design. So now, if I compare the beam, because in 5G and 6G technology, the beam steering antennas are also there. So the beam steering antenna, as I told you, I just discussed. So you can steer the beam in a particular direction, generally by using pin diodes we are used. So these are some of the advantages are there: reduce interference, conserve power, narrow focus beam. So the Butler matrix can be used. Butler matrix means just a type of matrix. So where you have a branch line coupler, phase shifter, and a crossover. So if let's say P1 is excited, so you will get some beam. So it is a branch line. So basically there is some mathematics behind that. So it is basically you have the 4 arrays, that is 4 element array. And if let's say P1 is excited, so if P1 is excited, so we will have, so they will have the phase difference. So you will have, let's say some phase difference will be there. So depending on 0, 45, 90 degree, 45, some, so you will have beam will be generated in a particular direction, because you know the if you are in array, if you feed with different phases, you can switch your beam, you can steer the beam. Similarly, if P2 is there, so you will have the another direction, P3 is in another direction. So this is the 2-directional beam steering antenna. So this is the hardware. I will skip it. So in the similar way, so if you can see that it is much more getting complex if you move to the higher number of beams. So here the means the beams, let's say it is something like 8 cross 8. So you have 8 input beams, 8 inputs are there. Only let's say if you want to get the beam 1, so I will just excite the feed 1 only. If I get the beam 2, I will excite beam 2. So, but hardware requirement is much more larger. Here it requires crossover, phase shifter, and the happy. All these things are required. Okay, so these are the some Butler matrix approach which are used for beam steering. Another is that you just feed it with so there is a dual polarized. I will just discuss. So it is just dual polarized antenna is there. So based on that, so they have so it is just a 16 something like massive MIMO. It is used for massive MIMO. So is massive MIMO structure. So the basically dipole antennas are there. So if you feed different antennas, so if you then your beam can be steered. So here they have shown beam can be that is at lower frequency and that at higher frequency means so beam can be steered in a particular direction means you can shift the beam, or you can generate the multiple beams depending upon the how much which port to excite. Okay, just I want to compare this RIS and this one. So the RIS basically, so no amplifiers, so power consumption is very less, but it has a high power consumption. It changed you can place in the environment. It has to be placed at the transmitter or receiver, but we don't know where your receiver or user is there. So it's reflect and reconfigure the incident wave to shape the wireless signal, but it just actively steer your transmit or receive beams. Okay, so mainly is that, so it is used as energy efficient environmental reconfiguration, and it is low and simple implementation. It is highly cost is high and implementation is high. So now in 6G, what it is not like, because we can use the advantage of RIS and beam steering just to compare these two. So the beam steering points a beam to in a particular action, or RIS, how to control them. So RIS, so what we can say that RIS, some people have asked if you compare these two, how to compare it. But RIS doesn't replace the beam steering, rather than it complements the beam steering by adding another layer of control to the wireless channel. Okay, so it is just controlling the wireless channel. If you use the combination of these two, that will be excellent, and people are going to use it. So in future sixth generation systems, so beam steering will focus towards the RIS beam steering antenna, and RIS will intelligently redirect the shape of the. So the smart, controllable, energy efficient wireless environment will be generated by use of the beam steering and the RIS. So now I will stop here. If you have any questions, you can ask me. I can discuss. Yeah. Hmm. Yeah, questions.
Sir, there are two questions, sir.
Yeah.
May I ask the question on behalf of participant?
You can ask, no problem.
Okay. So in which software it can be simulated with the programming and horn antenna as transmitter? And if CST can be used, then can you please show the programming to control in CST?
CST, I don't have CST. It can be used. Basically, you have to that is co-design is there. Okay, so first one is that so unit cell can be designed either in CST or in the CST or in the whatever the CST or in the HFSS or in the ADS also you can design it. No problem. Unit cell, because ADS is having the 3D EM simulator. You can design the but the question is the controlling thing you can design in ADS and in the CST. HFSS cannot, means you cannot design in the HFSS because HFSS doesn't take the discrete values, or there we don't have the option of co-design. But ADS is good. I think in ADS you can use it. No problem.
Okay, next question. Anandi, ma'am, you can ask the question. Participants can unmute themselves, Abhishek sir and Anandi.
Hello.
Yeah.
Sir, good morning.
Good morning.
Sir, can you please explain, as I am new to this RIS, actually I am working in FSS.
Okay.
And, this RIS, I have heard about it, but how that phase diagram, can you please explain me that diagram? Actually, I want to understand that.
Okay. Phase.
A plot where you have have plotted S11 and the phase.
Okay. Okay, my screen visible?
No, sir.
Okay. अब दिख रहे हैं? Now it is visible, I think.
Yes, sir. Yes, sir.
Okay.
I think the 48.
हाँ, ये यूनिट सेल था. This is the
हाँ
unit
सर,
cell.
47th
Okay.
number.
हाँ, yeah. ये जैसे है.
Yes, sir. This one.
So now उससे अच्छा ये देखो, little better. So
Okay.
if you see, okay, let me point to option. If you see, let's say you have designed the structure.
Okay.
So S parameter, if you see, observe the S parameter. So S parameter, what you will observe as magnitude, it will be just minus 2 dB you will get for all the biasing conditions of the vector diode. That is 1, 2. So 1, 2 is the, if you apply the biasing condition of the vector diode, so you will get this one. Okay.
Okay, sir.
ये
Capacitance.
bias, I want to have this capacitance. This capacitance combination will give me these states. If I draw a line here, so if you see, observe this point, this point, this point, this point, 4 points are there. So at the lowest point, you will have, if you see here, you will getting phase of 180 degree or plus 180 degree. Here you are getting a phase of 90 degree. Here you are getting the phase of 0 degree, and here you are getting the phase of 90 degree. So basically, the 4 states are there: 0, plus 90, minus 90, and 180 degree. The 4 states are there.
Okay.
Are you getting?
Yes, sir. Yes, sir.
4 states at same frequency, at
Yes, sir.
3.5
At
gigahertz.
3.5 gigahertz. Okay, sir.
3.5 gigahertz, you are getting same this one. So iska, you don't have any, iska koi mahatva nahi hai. It is not having any physical, just because it
It
just
shows
tells you
just
about
reflection. It just shows
just
reflection
reflection.
is
Yeah,
going
it is
on.
getting reflected. Yeah.
Okay, okay.
So once you got these things, let's say if I apply this bias voltage, so if I apply this, I will get this one. So these are for the first 4 states. Ye mil gaya? Clear or not, first of all?
Yes, sir. Yes, sir. Yes, sir. Yes, sir. Yes, sir. Yes,
Clear.
sir.
ठीक है. तो अब ये वही चीज है, that is same thing, just we have plotted on the, इसमें plot किया. अब इसका यूज कहाँ करेंगे? How, where to use it?
Yes, sir.
तो ये जैसे ये है. So this is what we have. We have 20 cross 20 RIS unit cell. First you have to calculate how much phase do you need for let's say phase. जैसे यहाँ पे ये phase calculation किया है. ये भी 20 cross 20 unit cell है पूरा. So if I want to have a, that is, if you see here, that is theta equals to 0 degree. I want my beam to be transmitted into 0 degree. So I must have this phase of nearly about at center में 180 degree. यहाँ ये वाला, ये मिलेगा. उसके बाद ये वाला, that is 270 और 180 degree, यहाँ ये वाला phase मिलेगा, ये पूरा. तो तुमको जो भी whatever the phase जो हमने वहां पे जो चूज किया था, तो जो डिजाइन जो ऑप्टेन किया ना, 0, प्लस 90, माइनस 90, 180 डिग्री, तो इन्हीं को ये जैसे 0 डिग्री, ये 4,
हाँ,
ये
सर.
5, बेसिकली 4 स्टेट से. तो अब तुमको ये अपना अरेंज करना पड़ेगा. यू हैव टू अरेंज मतलब अपने यूनिट सेल को, या तो बायस, ये ऐसा बायसिंग लगाना पड़ेगा. अब इसकी इंफॉर्मेशन कहाँ से मिलेगी? यू विल गेट इंफॉर्मेशन फ्रॉम दिस इक्वेशन. ये इक्वेशन है, ये हम लोगों ने ये फेज डिफरेंस इक्वेशन.
Okay, sir.
This phi equals to, ये book है पूरी, that is book is there, phase difference. Phi equals to k times ri minus r naught plus phase. बेसिकली क्या करना होता है, मान लो जैसे ये एलिमेंट है, मान लो. सो इफ यू हैव अ हॉर्न एंटीना, तुमको 0 जो यहाँ का बेसिकली क्या है, यहाँ का जो सिग्नल जा रहा है, ये पूरा सीधे ट्रांसमिट करेगा. यहाँ वाला सिग्नल, ये क्या फेज डिफरेंस ज्यादा हो गया, तो क्या हुआ, फेज डिफरेंस, क्योंकि यहाँ पे फेज, और तुमको बीम को इधर ही पॉइंट करना है, तो तुमको उस हिसाब से फेज डिफरेंस यहाँ पे देना पड़ेगा. क्योंकि और लार्जर वाले में दूसरा, ये चीज फिर इधर जाएगा. यही चीज अगर इफ यू ऑब्जर्व दीज थिंग्स एट, मान लो अभी ये यहाँ पे, मान लो लेट्स आई विल मेक इट कंट्रोल दैट, आई विल if you want to add another frequency, so यहाँ वाला क्या है, let's say whatever, if you see here, this is, if you see the, for 0 degree, it is having the same thing, 0 degree. लेकिन as soon as I want my beam to the another direction, so what I should do, I should change the phase. यहाँ पे पूरा phase change करना पड़ेगा, phase
Okay,
change
sir.
करना पड़ेगा. तो ये देखो 0 डिग्री का सब में सिमिलर है,
Yes, sir. The
और
color
सबका
white.
चेंज करना. हाँ,
Okay, okay.
मतलब चेंज, you have to change the phase because जो जा रहा है उसको तुमको डायरेक्शन को चेंज करना है. तो that you need to understand how much phase you need to change, that is required.
Okay, sir. Okay, okay.
Okay, so ये आसान नहीं है, you have to understand it and do it. ये पहले
Okay, sir.
समझना बहुत जरूरी है. इसके लिए you can screenshot ले सकते हो, और I will share that is, this book is there, so this book is there, so there they discuss how to do that.
Okay, sir. Okay.
Very thin book है. Okay.
Okay, sir. Okay. Thank you, sir.
Okay. Thank you. Yeah. Another question?
Sir, participant is asking to if you can kindly give the details of 3D printing procedure.
3D printing तो easily available हर जगह है. Okay, ठीक है. Okay, just I will tell you. So, okay. ठीक है. See, okay. So you can get the 3D printer in 50,000 rupees. 50,000 में अच्छा मिल जाता है, या और whatever. See, 3D printing में क्या है? So it is, see, it is just as I told you. So you have to get different phases. अलग अलग phase निकालना है. अलग अलग phase के लिए base तुम्हारा, you have the same base and dielectric material is different. दूसरा dielectric material. So dielectric material, you know, डायलेक्ट्रिक मटेरियल जो भी तुम्हारा PLA पॉलीलैक्टिक एसिड मटेरियल अवेलेबल रहता है, उसकी 3D प्रिंटिंग करते हैं, लेकिन यू डोंट नो द इलेक्ट्रिकल प्रॉपर्टी ऑफ दिस डायलेक्ट्रिक मटेरियल. उसके लिए क्या करते हैं, बिकॉज वंस जो भी तुम्हारा मटेरियल है, सो फर्स्ट यू हैव टू डू द निकोलस रॉस वियर मेथड, जिसमें क्या करते हैं, यू नीड टू फाइंड आउट द डायलेक्ट्रिक कांस्टेंट एंड लॉस टेंजेंट ऑफ दिस 3D मटेरियल. कितना लॉसी है, क्या उसका एप्सिलॉन आ रहा है, क्या tan डेल्टा है, ये निकोलस रॉस मेथड से वेवगाइड के अंदर अलग अलग सैंपल्स बनाकर यू हैव टू मेजर द एस पैरामीटर. उसके बाद पूरा एक्सट्रैक्ट करना पड़ता है. देन यू विल गेट दी tan डेल्टा एंड दी डायलेक्ट्रिक, दैट इज tan डेल्टा एंड दी एप्सिलॉन आर ऑफ ये tan डेल्टा है, एप्सिलॉन आर म्यू आर. यू विल गेट ऑल द थिंग्स. तो ये यू विल गेट ऑल द प्रॉपर्टीज. You will get the properties. Once you know these things, then you can easily design using 3D printing. 3D printing can be easily, if you have the structure, you can ask, industries are there, so they are able to do that. But they don't know the material, so material के लिए just buy a 50,000 में printer मिल जाता है. At least you can do some sort of work at the lower frequency. You can do that. Okay. Anything else?
Participants, if you have any query, you can ask. Sir, one question from the participant, that how can we choose the particular type of the diode or the value of the capacitor and resistor that we should use?
So that is that comes from the error and trial, or that you have to apply it and check it, because इसमें whatever you have to apply the bias voltage and check it, and you will get few papers. Diode also, depending on the application, means you see at, let's say this diode is, means see the data sheet of the diode, whether it is data sheet is means whether it is using, or means whether it is, this diode is working at high frequency or not. If it is not working, please don't use it. Then if it is working at high frequency, then you can use it this diode by data sheet. और ये तो तुमको they will know these things by applying them. Means just पहले first you design simple patch में just load the patch with some directed diode or some capacitance, then you will see the change in the frequency and the phase and the frequency, because phase और frequency दोनों change होगी, because we have seen the frequency भी change हो रही है, phase भी change हो रहा है. Okay, then you can understand. Yeah.
Okay, sir.
Anything else?
Any more questions, participants? Sir, I think there are no more questions, sir.
Okay.
Sir, may I also ask one question, sir?
Yes, sure.
Sir, that for the massive MIMO, more antennas are required. More than 200 antennas are required. Correct, sir?
Yeah.
But being like a research scholar, and we are working on the massive MIMO. So maximum, how much antenna that we can take, and it can be accepted as a massive MIMO?
You can see, you can take this as a, show that as a 4x4 or 16x16.
Hmm.
Okay, I will just show you. Wait. Okay, in this paper, if you see, just this one. So this is the, basically, they have demonstrated for the 4x4 or 16 unit element.
Sir, your screen is not visible, sir.
Okay, wait. So now it is visible.
Yes, it is visible.
Okay. In this paper, I will just show you. So this paper. Okay, wait. Okay, this paper, they have used the dipoles. So they have fabricated the 16, that is 4x4 massive MIMO. They call it massive MIMO. But so that is more than enough. But for, let's say, if you want to, once you have the beam forming capability shown in the 4, that is in 4x4, you can use some software called VSA. That is VSA software is there. So that can be used. So they have shown the beam capability 16x16 top dipole array. So the software can be used to demonstrate the beam forming capability. If you see, if you observe here, the beam width is larger, but because of the using the 16x16 or large, that is, it has 256 element. So you can observe that it will have the narrower beam. You can use it. That the VSS software is there. That is provided by the Agilent. Are you getting?
Yes, yes, sir, I'm getting. So, some people says that for the MIMO connected grounds are required, and some papers claim it's not necessary to have connected grounds. So, can we take both the things or connection of
Both
grounds?
generally connected grounds are required. Most of the people say that the connected grounds are required. Ground must be common.
Hmm.
Then what is the difference between two different isolated antenna if ground is not common?
Yes, sir.
Okay.
Any more questions, participants? Sir, I think no more questions are there.
Okay.
Uh, On behalf of EICT Academy, MNIT Jaipur, and Electronics and Communication Department, MNIT Jaipur, thank you very much, sir, for accepting the invitation. The session was very much useful, and I hope the participants also learned a lot of things from your research and your experience, sir. Thank you very much for sparing the time and accepting our invitation.
Okay, thank you. Thanks a lot. Thank you.
Thank you,
Thank
sir.
you, Swati. Thank you, Sarthak, and thank you, Reena.
Dear participants, our next session is from 11 a.m. Session 2. You are requested to kindly stay connected.